So going back here, we know that our emitter is going to be grounded, right? Because we have this ground here, so we ground ourselves there. Okay. We know that this is going to be our V out, right? So what we can do is just replace this, call it V out, and now there's a few things here. We need to figure out what do we do with this RC and how do we approach this block here, right? So we know our V in is AC, purely AC, so we know that's going to stay. Okay, so if we can draw that like this is V in. Okay, now let's consider this, DC bias here, right? It's always going to be 0, okay, in time, right? So VB, this is our large signal, right? It's always going to be 0, so we're not going to change in time. Okay, so effectively, because we're not changing in time, there's no voltage difference, right? So because there's no voltage difference, it's going to be grounded. So in other words, if there's no voltage change across, some point, some node or some element, there's no voltage change across it, then that's effectively a ground when it comes to AC analysis, or not AC analysis, sorry, our small signal model. Okay, so 0.7 volts doesn't change in time. So what that means is, hey, it doesn't change time, has a drop of change in time of 0, and 0 is effectively, well, our ground. So it becomes grounded. And kind of a similar idea with the RC. We see that RC is tied to V out. Okay, so RC is going to be here. RC is tied to VDD, and VDD is typically going to be 5 volts, and again, doesn't change in time. It has a change of 0. So it has a change of 0, meaning that this node of our RC doesn't change. It has change of 0. So that's going to be now tied to ground. And these are all the same grounds. If we want, we can now kind of connect all of these together as one ground. Do something like this. Okay, so, in white we have our basic BJT small signal model, and in red is just the additional stuff. Okay, cool. So the best way of viewing this now is to just write a few equations out. So just like lecture, we know V pi is going to be equal to V in, just from the KVL on this left loop. And now we know that, V out is going to be equal to negative, well, got ahead of myself there, is going to be equal to RC times, whatever current is going this way, right? Because we reference it like this. So we know this current going this way is going to be negative GM V pi, because this goes in this closed loop here. So we're going to have RC times negative GM V pi, which is going to be equal to negative GM RC V in. So in our gain, is going to be V out, or V in, negative GM RC. Okay. Now, if we add the early effect in here, what we're going to see is we're going to see another resistor here. I'm going to rewrite this here, GM V pi. Another resistor from our collector called R0 from the collector to the emitter. Okay, so we connect this now to our emitter, and just for clarity purposes, our emitter is ground, so I'm just going to draw it down here. So now, see that our gain becomes negative GM times RC parallel with R0. Okay, and these equations are also in the lecture notes I posted. Okay, so hopefully that kind of makes sense. This notion of taking our DC nodes, as VDD and the 0.7, and making it ground, and things that are AC that change in time stay the same. Okay, and that being said, if we have another resistor at our emitter, if we were to have another resistor, let's interpret our small signal model as well. So moving on back to emitter degeneration, which helps to solve beta and temperature variation, we have this as our now small signal model, and I'm going to ignore R0 here. It just kind of complicates the math, and typically we can ignore it. R0 just gives us a good idea of what's the max gain we can get out of an amplifier. So in this case, it's kind of fine to ignore it. We don't want a super exact analysis. After all of these equations are approximations themselves, right? So just get a notion of what's happening to our gain. Okay. So we now have this RE in here. So we can see, okay, it's still our emitter's here. It's no longer tied directly to ground. We have an RE in the way. So that's all the change that was made. Okay, and of course, no R0. So we can go through, we can do the same analysis, a bit more complicated KCL, KVL, and we'll get that V out over Vn, which is our AV, is negative GM RC over 1 plus 1 over R pi plus GM times RE. Okay, and we know GM R pi is typically going to be, greater than 1, which means GM is going to be greater than 1 over R pi. So this denominator just becomes 1 plus GM RE. So we get negative GM RC over 1 plus GM RE. And just to verify this, you can plug in RE equals 0 and get the same gain equation as above. Okay. Now there's still this, notion that it doesn't remove variation of beta and temperature. It negates it. Okay. So beta can still vary just due to different manufacturing processes. Temperature can still vary. These in turn change our R pi and our GM, right? Which then changes our gain. And they can change quite a bit by around 5 to 10%. If our BGTs are not manufactured very well. But because we now have this RE here, these effects are no longer as noticeable. So we typically want this degeneration resistance, as it helps make our systems more, predictable. When we make an amplifier, we don't have to worry about as many, process issues. We use one BJT versus another, we want to get similar gains. So it kind of reduces that effect. Contrast of this is that we have, a lowered gain, and that's typically not ideal. But when we talk about circuit design, there's always going to be a bunch of tradebacks to, what we do. So we try and work with what we have. Okay. Next thing that I didn't really get to talk about too much during the lecture that I'll touch up on here is just how we bias, a BJT amplifier. Okay. So over here, looks a bit more complicated, right? We still have the same RC and RE here in our common emitter amplifier here. There's a few new things. We have this R1 and R2 here, and we have these two capacitances. All right, so we'll quickly kind of talk about what's happening here, okay? So over here from before, you saw that we biased our base with our DC 0.7 volts, and we applied our input signal on top of our VIN on top of that, okay? There's a very similar concept going on here, okay? We want to bias our base still, okay? We still want to have it at 0.7 volts. So to do this, we employ a voltage divider from our VCC to do so, okay? So what this effectively does is it'll say our base voltage is going to be R2, right? So R2 over R1 plus R2 times our supply, which is VCC. Okay, that's how we take care of this base biasing, right? It's the same. If we want to make this 0.7, we'll figure out the values of R1 and R2 times, VCC of 5. That makes it 0.7. Same effect as that thing over there. Okay, that's all that does. Now the next thing you'll see here is we have a capacitor here, okay? So one thing to note is, typically when we make amplifier stages, when we make amplifiers and analog and RF design, we typically have several stages kind of cascaded together. You string them together just like maybe in 102 you've talked about, transfer function, having different systems following each other. Same idea, okay? When we, at least in RAP, we're considering, we want to be able to we consider 1 megahertz waves from our MCU, going that up, scaling it up to 5 megahertz, scaling it up to again 27, sending it out to an antenna, right? When we send out these frequencies, right, if we have like a 27 megahertz wave, it's going to be a pure sinusoid, so there's no DC bias, right? We want to send out any DC. We want a pure AC signal, and this is typically referred to as an RF signal. So RF signals don't have any power, okay? That's the main point. There's no DC power, okay? So what this means is that if there's, this V out, let's say, is connected to our antenna, right, you're going to have some sort of DC and AC wave here, right? DC because we have our large signal IC over here, right, and that's going to create a voltage drop across this resistor. So the voltage at DC voltage at this node is going to be VCC minus IC RC, right? On top of that, we're going to have our input signal here. We're going to have our VIN times AV, right? And this is just V out. So at that node over here, we have DC and AC, okay? This capacitor is going to block this DC component, such that our V out now is purely just VIN times AV, just our AC signal, okay? So that's what that capacitor does. And very similar case on the input side, we have a DC biasing network here that'll make Vx 0.7, right? And we have this AC signal, presumably from some previous amplifier stage. We don't want this DC to go back and interact with the biasing, right? If we have another amplifier stage, this Vin would be where this Vout is, right? So then if there's DC here and there's no capacitor, it's going to now bleed through the previous network. So we don't want that. We want to isolate these two. So that's what this capacitor does. It stops this biasing here from going back into previous stages. Okay. So one way you can now kind of look at this, if you were to draw, a diagram, would be, this is our Vn. It's an AC signal, DC value of 0, and it has a certain peak voltage. Okay. Now our node at Vx, which is that node right there between R1 and R2, this is going to be at R2 over R1 plus R2 times VCC, and that's typically going to be greater or equal to 0.7. And this is going to have, Vx is going to be Vin plus R2 over R1 plus R2 VCC, right? So it's going to have the same AC wave over here added onto the 0.7 bias, right? Same as this situation here, okay? Next thing over here is we're now going to look at the collector node, okay? So this is going to be VC, right? Now we have the same DC bias, VCC minus ICRC, right? I hope that's clear. And now we amplify our input, right, by AV. So we said our peak value of our input was VP, so now we multiply that by AV, which is this green wave here. That's superimposed on top of our DC, VCC minus ICRC. Next, after this capacitor, it blocks the DC, so it just takes this AC wave and shifts it back down to 0. Okay? So, we added these two capacitors. That's great. It helps with the biasing, also decoupling our AC and DC, right? Next thing we want to talk about is, how does our R1 and R2 change our small signal model, if at all, right? So, again, just looking at the normal common emitter amplifier with the RC, right? This is all the same, right? Hopefully this is all the same as before. The only new things are this R1 and R2, okay? If we look at our small signal model over here, right? Let's just assume we have, this is still Vn, right? Our AC signal is here. Ignore this as this capacitor. Our assumption is that, at this frequency of interest, this capacitor is like effectively a short, okay? And because of that, we don't look at that, okay? The other way you can look at it is just we can split it up like this and say, we don't look at this capacitor at all. We just look at this network here, okay? So that's what's happening there, okay? So we just see our same phenomenon as before. Our R1 is connected to VCC, so it's going to be grounded, hence this ground. And our R2 is connected to the normal ground, so it's still going to remain at ground, okay? So if R1 and R2 are large, then, we can treat these guys as, open circuits. No current is going to flow from here, right? All of it's going to go there. So if that happens, then, it doesn't change our model at all. We still see this R pi, RE, GMV pi, and RC, just as we showed right over here, right? This network here. Same thing. But if we don't ignore them, what kind of happens, okay? So generally speaking, if they are large enough, then our input and output impedances remain the same, our gain remains the same. But if they aren't large enough, then they'll show up in our input and output impedance, and they'll change our gain, okay? So remember that we care about using R1 and R2 for biasing, more specifically the ratio of them. So, R1 and R2, you can have them maybe be, let's say they're both 10, right? Then your VB, your base voltage is going to be, 10 over 10 plus 10, which is 10 over 20 times VCC, so it's going to be half of VCC. So it's going to be like 2.5 volts, right? We can also use R1 and R2 being 10,000 and get the same ratio, right? So we care about the ratio of the two, just the voltage divider, okay? So you typically want to make R1 and R2 very large so that they don't show up at all in our small signal model. In other words, again, no current goes in, we can assume they don't even exist, right? But otherwise, they're going to show up in our gain, and they're going to result in less current, less of our input signal, right, reaching our R pi here. We're going to have current going away from these nodes here, going to R1 and R2, which is going to decrease V pi, decrease this current here, and decrease our overall gain, okay? So what happens here? All right, the next thing I'm going to talk about is loading. And the reason I bring up this R1 and R2 biasing is because on one of the one of the assignments on the module is talking about, make an amplifier stage that has a certain gain, has a certain input resistance, and I believe a certain output resistance. Okay, and input is going to be pretty large. That's great, but you'll realize that you can get the right gain out, but then you're not going to be able to match the output resistance for typical values of R1 and R2. You typically want R1 and R2 to be in the 10,000 range, right? So if you use values in the 10,000s, you're going to find that you can get the gain correct, which is great, but you can't match the output impedance, right? And you should recall that. Let's see, where's the best diagram here? Output impedance is, hey, if we look this way, what resistance do we see? So what resistance do we see looking into the collector, right? So we'll see this RC in parallel with whatever we see looking down, right? So we're going to see some RC parallel with, it's called R prime, where R prime is looking down to this network, right? So we'll see that there's a trade-off there. And the solution to this is you have to now lower your R1 and R2 so that they show up in your output impedance equations, and there's no need to derive it. It's just one of those, like, while you're in LT Spice, the goal is, okay, you get the right gain, but now you're not able to get the right output impedance. Let's now try lowering R1 and R2 so that they show up and start to mess with our gain and output impedance. And eventually you'll find a ratio between R1 and R2 and RE that allow you to have the right gain and the right output impedance. And typically this is just like an iterative process. There's no need to derive exact equations. Just keep messing with these values, and eventually you'll get it. But there's no exact need to do it. The main thing we care about is getting the right gain. And as we'll learn in later hardware lectures, we'll see that if we have something that's like 50 ohms and it looks like 50 ohms, and then now we connect it to like something that's like, I think if you use the normal values of R1 and R2 being in the 10,000 range, you might get like 45 or something like that. You're going to have an impedance mismatch, which means you're not going to get a maximum power transfer from this network, from network 1 to network 2. Right? If network 2 looks like 45 ohms, network 1 looks like 50, you're not going to have an optimal power transfer. So we'll talk about different ways of accounting for this. How do we make this 45? What can we insert here that makes this 45? What block can we insert here that now makes this look like 50 ohms, right? So that's why it's not that big of a deal if the output impedance doesn't match, because we're going to talk later on about how we can remedy that. The thing we can't remedy is if we don't have enough gain, right? If we don't have enough gain, then we have to add a whole new amplifier, which introduces various other issues. Ideally we want things to be as good as possible when we make them. So that's a general idea. So as you're going through that module, the main thing is the gain, but if you have time, mess around with R1 and R2, see how, as you take them from very large values to small values, how they kind of interplay with your, your R out, your RA, and then your gain. Okay. So next we're going to talk about is loading, right? So we'll take the same biasing stages before. There's R1 and R2 as a voltage divider, and we assume there's some caps, etc. here on the input. We don't really need to concern ourselves with that for this. Okay. Now we're going to talk about, let's say we hook up some microphone here, or rather like a little speaker. Okay. All right. This has some load resistance RL. Right. So as before, we can say R1 and R2 is large enough, and we assume that they have biased our base such that our base emitter, this here base emitter is 0.7 plus, right? And we also still assume that VCC minus ICRC is going to be our collector voltage, and that's collector emitter voltage is going to be greater than 0.2. Okay. So now what happens is, okay, we see our RCs in parallel with our RL, and we can kind of just equate those two together, right? Because they have the same node here, and this in our AC signal becomes ground, right? So they effectively become parallel. So we can just make a simple modification to our previous common emitter degeneration formula and just substitute RC with RC parallel RL, right? And we know whenever we have two resistances in parallel with each other that we're always going to get a smaller result out, right? So our gain is going to be smaller than if we just had no load resistance at all, right? If RL was, infinity, if we have two things, let's say we have RC parallel infinity, things in parallel prefer the smaller ones to the output, right? So this is going to just be RC, right? So that's just gets us to our equation from before, as if we didn't even have that speaker to begin with. So, we talked about this in lecture. We're now going to insert a buffer that isolates our output, our speaker, this VC node here, from our load. We want to use a buffer that isolates the output of our amplifier from our load. Okay, so we want to have something here that blocks this connection. Okay, so we kind of talked about a buffer. Our common collector buffer here. It's a very standard topology, and we said the gain is going to be RE over 1 over GM RE, and I would hope all of you kind of go through and you apply the same small signal model. And one thing you should notice, small signal always assumes run forward active. So you can't use small signal model if you don't bias the transistor properly, okay? And at the end of this lecture, I'll talk about the usual design flow for designing an amplifier, which will help you for your module. So going on, if RE is much greater than 1 over GM, we get that our gain is roughly 1, okay? In reality, buffers are typically going to have a gain of 1/2 or 1/3, which is not as good as 1, but they still provide very good characteristics that we can employ as a buffer. So if we do our RN, and this is something that you can also do in your own time or look online, it's going to be R pi plus beta plus 1 RE, right? So RE is already going to be much larger than 1 over GM. We know RE is large, and beta is going to be 100 to 200. R pi is typically in the thousands, so RN is going to be very high. Okay, in fact, it may even be comparable to R1 and R2. That's how large it could be. R out is going to be 1 over GM parallel with R pi. So that's going to be a very small value. Okay, so what we can do now is if we place this, if you have like an amplifier, and we place this buffer, place this load, right? If we look this way, right, this is our new R load. We'll call it R load prime. Okay, this is going to look very large, right? Which means that if we go back over here into this equation, we plug in the large RL, we're just going to get negative GMRC as a numerator. So that's good. Okay, and then consequently, hey, if we look this way from our load, we're going to see a very small impedance. And what this means is that there's going to be a more direct connection, right? If we have a large impedance we see a large impedance, that means like we have more like resistance in the way. So we don't want any impedance looking back from the load. And we can never actually get 0, we can get it very small, but we work with what we have, right? Ideally, we want to make RL prime infinity, but we can't, right? So that's what our buffer does, okay? Now, going back, is there a way to, maintain our large gain while still having the beta and temperature stability that RE provides? Because from before, RE is great for stability, but lowers our gain quite a bit, right? Just going back to the common emitter amplifier, okay? So let's just consider a few things here. All right, let's consider we just have one resistor versus the same resistor in parallel with a resistor that's 1/10 its value. If you look at this input impedance here, you see that Zn is just R, right? And that should be very straightforward, I hope. And then now if we do Zn over here, we see R parallel with 0.1 R, right? And we can do the math out and we get 1 over 11 R, which is pretty much very close to this lesser resistance, right? So this is very common when we design things, is that if we want two things in parallel and we want that output to be the smaller one of the two, it's a good approximation to make the second thing you add in parallel 1/10 the impedance of the first to get it to be equal to the impedance of the second. Okay, so we want 1/10 of R roughly to make this good approximation. And 1 over 11 R is roughly 1/10 R. Okay, so that being said, when we talk about in RAP, we operate different frequencies, right? We want to amplify a 1 megahertz signal at some points, we want to amplify 5 megahertz. Then right before we send it out to an antenna, we want to amplify our 27 megahertz, right? So we want high gains at these frequencies, and ideally, we want a lower gain at other frequencies. In other words, we want the maximum gain at this frequency, right? So if we look in the frequency domain, don't worry if you're not super familiar with this. If we just have, a frequency that looks like this, right? We have a constant, let's say, let's call it constant power across some frequency span, right? And we feed this into an amplifier. Ideally, the amplifier is going to, amplify all of these, right? Ideally, make it not, we want to design our amplifier such that it has a maximum gain over here. Okay, so it amplifies at omega naught the most. Okay, so it's in a way like a filter. You can think about it like that. It doesn't actually attenuate, but it, in a way, isolates our frequency of interest from others. Okay, so that's what we want to do. So how could we do this now? How could we still have high gain and 1 megahertz, 5 megahertz, 27 megahertz? And the way we do so is by minimizing RE, right, in our AV equation. We can find a way to minimize RE, our emitter resistance, at these frequencies, then we get this scenario here. Okay. So what do? We insert a capacitor at our emitter, so that at our target frequency, Ft, the impedance of this capacitor is going to be 1 over 2 pi FTC, where C is the capacitance. And this is going to be 1/10 of our emitter resistance, right? Same concept over here. Okay, so what does this look like? Looks like this network here. And I guess I'll draw this on the side. So what this looks like for our normal BJT structure, it's going to be something that looks like this. Okay, RE. Oops. Let's make this going to ground. My pen's not erasing. Nice. Okay. It's going to look like something like this, right? And then at, mega naught, just 2 pi F naught, this capacitor is going to look like 1/10 RE, at which point we just get, RE in parallel with 110 RE going to ground, which, looks pretty much like 1/10 RE. So it's going to be a lot smaller, right? The same concept from over here. Okay. So that's what we do. We apply the CE in there. And to determine its value, you just apply this equation here, right? Now, it doesn't have to be 110. You can make it, hey, 1/100. But 110 is typically a good rule of thumb to follow. Okay. And, now we can just put our assembled picture together. So over here we can see we have our R1 R2 biasing network, or RC, so we can have some sort of gain, RE, so we have more stability, CE, so we can have less emitter degeneration at certain frequencies. And the term for this is a bypass capacitor, because if we look over here at let's say 1 megahertz, let's say at DC, right? At DC we're going to see this is going to be an open, right? DC is going to be an open, so no currents are going to go here at all. So DC we're just going to see RE, right? If we look this way, we're just going to see RE. Let's say at omega naught, right? We're going to look here and we're going to see we're going to see 1 over 10 RE. We can be more specific, say 1 over 11, right? So the general idea is that as our frequency increases, more of our signal is going to go to the capacitor. So initially, all of it's on the resistor, and as time goes on, more of it's going to bleed through to using the capacitor. And eventually, at an infinite frequency, this capacitor is going to be a short, and all of our signal is going to go to all of our current. Okay. So that means we're not going to see any emitter impedance, right? Which takes us back to just a normal, common emitter amplifier with no emitter degeneration. Okay. So it's called a bypass capacitor. These C1s and C2s, I hinted at what they are before. They're called decoupling capacitors, and they separate AC from DC. And we have our purely sinusoidal VN, purely AC VN, going to our C1, our R1, R2 voltage divider biasing network. We have our Q1, Q2. This is our amplifier stage, right? All of this amplifier. Okay, that's going to be fed now to C2, which just isolates our, again, DC to AC. That's going to be fed into our buffer, and that's going to now be fed out to V out and out our load. So a few things to notice. Typically, RE2 and RE1 are not going to be the same. RE2 is going to be much larger than RE1 typically, just so that we can get RE2 is going to be much larger than 1 over GM. And we're going to assume Q1 and Q2 have very similar, characteristics. So their GM is going to be similar. So we typically want, we want a larger RE2 than RE1 typically. And this is, of course, case dependent, but that's typically how we want to design things. Okay, so now we've quickly talked about that. Let's talk about, I'll give you a bit more insight into how do we, design an amplifier. Okay, first things first, when you are given, hey, design an amplifier, and this is something you'll see in the modules as well, is first we need to make sure it's in saturation. All right. So I'll go through 2 cases here and nothing more than that, but I'm hoping that it'll be kind of helpful. One, and I'm going to ignore these capacitors here on the input. I'm just going to assume it just goes straight to well, the capacitor is going to be there. We're not going to include that in our analysis. Okay. So our AC in and then our V out. Okay. First things first. This is going to be VDD. Okay. Sorry, VCC. Okay. First things first is we want VB before we can apply any small signal model, right? Maybe the module, I believe it wants a gain of 20. I could be wrong. Maybe 50. Before we can even talk about, hey, what gains do we need, blah, 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 right? We need to determine what region we have to operate in, right? We know we have to operate in the far active region, so VBE 0.7, and we can do this by saying, hey, R2 over R1 plus R2 VCC, right? We can solve for R1 and R2, come up with some values, right? Now, the next thing we want to do is make sure our VCE SAT, our VCE is going to be greater than VCE SAT. So typically VCE minus 2B 0.3. Okay, and well, what this does is it places a limit on how much current we can have here, right? If this current is infinite, or rather not infinite, but let's say it's very large, right? Then we're going to have, let's say we have a 5-volt drop across this resistor, right? 5 volts, and VCC is 5. So that means we have 5 volts VCC minus 5, so that means our collector is going to be at 0. Oh wait, if collector is at 0, collector to emitter, VCE, now going to be 0. Alright, that's on 0.3. So what's happening here is we're now going to have VCC minus IC RC has to be less than 4.7, right? Minus IC RC is less than 4.7. Okay, that's great. That's our large signal biasing. Okay, next thing we're going to talk about is, okay, what's the gain? Let's say we want a gain of 10, right? And we know from this topology that if, okay, let's assuming R1 and R2 are large enough, they're not going to come into play. These decoupling capacitors don't come into play, so we know our overall gain is going to be negative GM RC. It's going to be equal to 10, right? And when we say AB is equal to 10, I mean like the magnitude, right? So it's going to be positive, okay? And we know that GM is going to be equal to IC over VT. And this is the same IC over here, okay? So this now means we have IC RC is going to be equal to 10 times VT. So now we have two equations. We have this equation and this equation. Two equations and two unknowns, right? IC and RC, right? And this equation gives us a relationship here for the multiple of IC and RC. And this gives us, an inequality, right? So there are going to be numerous solutions to IC and RC here that satisfy these two. Right? We're going to have a whole plane of solutions, right? Because we have this inequality here, right? So in other words, we're going to have an infinite number of solutions for IC and RC that satisfy this. Now let's say so what we end up doing, and this is something I can talk about later, or those of you who are curious, is we typically want our collector, this part here, to be at half of our supply. And the reason for this is from before. Okay, if we have right over here, if VCC minus ICRC is going to be at, I guess I'll draw it over here so it's a bit more even. If that's going to be over here, right, VCC minus ICRC, and 5 volts is here, what this means is now sinusoids are perfectly symmetrical, right? So if we take this green wave and we add it, okay, we can have something that looks like this. Oops, sorry. It looks like this, okay? So we still have some room to amplify it before it hits these limits, right? And of course, because amplifying is symmetrical, sinusoidals are symmetrical, right? They have this VP here and this negative VP. So now this means we can have more headroom, right? We have the same exact distance from 2.5 to 0 and the same exact distance from 2.5 to 5. This means we can go all the way here, all the way back. In practice, we don't actually want to even go close to our supply because our device will turn off, but it's the general idea as to why we bias at the middle of our supply voltage. Okay, so this is back over here. So that gives us our second equation, VCC minus ICRC should be 2.5 volts. Now we can solve these two equations and get appropriate values for IC and RC. And that's pretty much it. Okay. Next scenario is if we have the same thing, RC, NPN, right, Q1, RE, and CE, and I'm not going to go too much into this. In fact, let's just consider same topology, right? Same R1, R2 biasing, right? Same idea applies here. We'll have the same notion of, okay, what's our AV, and I apply our equation, solve for GMRC over 1 plus GMRE, right? And that won't be GMRE, it'd be GM times this impedance here, but let's say just RE, right? So negative GMRE, right? So now what happens? So GMRC over 1 plus GMRE, right? So, from before we saw, okay, let's have our collector at what's it called, 2.5. Still typically follow that, but I believe in the spec they say to specify, our emitter at 2.5, right? So that's typically also what's done, is emitter being a 2.5, and from your VCE SAT that our collector then has to be like 2.8 minimum. Same thing. It just instead of the collector, you're just saying, okay, let's put the emitter at 2.5. Okay, that's a general idea, and as to why we bias it in the middle of our supply. Okay, and typically the same idea applies for buffers as well, because you want asymmetric response. You want to be able to have more room to play with to amplify. You don't want to, if you bias at 4, this is 4, and that's 5. You're only limited to signals like this. You can't really amplify any further. Oops. Right. That's the idea. So I guess, yeah, so far we just kind of went over, hey, how do we bias things and get to a point where, we can better understand, okay, we need to, before we can even consider anything like gain or small signal, we need to first make sure our transistor's in forward active region. We can't do anything without that. That's the first step, okay? So first step, forward active region, okay? At least come up with equations that dictate, the region of operation, right? Sorry, not that equation. That's gain. That's after this equation. Second step, assuming in far, apply small signal model and find gain. Right? In this problem, I said the gain was 10, but maybe you want to find the gain given certain RC/IC values, right? So once you can probably come up with an equation for your gain that consists of the IC/RCs, and then from there, you can relate that back to GM and R pi, which you can relate back to, large signal IC. And then from there, you'll have a system of equations, and you can mess around with the values, okay? And I believe in the module, you have a very similar problem to this, to design, common emitter amplifier, and you want a certain gain, so come up with a certain RC and IC that do so, right? And you also have to mess with, output impedance, which means your R1 and R2 will come into play, potentially. That's something you have to do, but we would like you to also just mess around and get a feel for how R1 and R2 come into play and what values come into play relative to your RC and your RE. Okay. I believe that's all. Some of these things I wasn't able to touch on during the lecture, and now that I'm feeling a bit better, I'm glad I was able to go through and reiterate. Yeah. Okay. And for the module, don't worry about exactness. Again, all of these things here that we've done are all approximations. Okay. They're all approximations. Like even these things here are just approximations, right? So if you don't get exact, module specifications, that's fine. We expect something, close to it. If we're expecting 50, 40 won't pass, but like 49, 48, 52, that's fine, stuff like that. It's all relative, but try to have as close of an answer as possible. I've gone through it, so I know it's doable, so I'm hoping that all of you can get close to that as well. Okay. I guess there may be one more thing to mention. In that we typically use a lot of bypass capacitors and decoupling capacitors. And the main things that you should know if you are confused by any of these impedance things is capacitors are going to be open at DC, right? So they block DC. High frequency, they'll be a short. And you should probably know their impedance equation, hopefully. And you should also understand how we have this RE in parallel with CE, how as I sweep frequency, how much of my current goes from RE to CE. At some point, the impedance of this capacitor CE will equal that of RE1, and the signal will be split both ways, right? Just like a typical voltage divider, or sorry, current divider in this case, right? But it's a general impedance concept that hopefully all of you should be familiar with. But if you still kind of confused on that, please reach out to either Grace or I. Regarding that, I believe, yeah, please watch David Baum's video on walking through LT Spice. He has some very good examples in there that'll get you familiar with different types of analysis that you can do in the LT Spice. That'll help us for designing amplifiers and just general analog design. Okay. For any questions, yeah, reach out to Grace or I. I'm hoping this has been a bit more fruitful and demystified some of the module. But yeah, apart from that, I think we're good. Next hardware lecture, we'll be talking about oscillators, so we'll talk a lot more about these amplifier structures and how we use them in oscillators. So I hope all of you are able to do the module by then, but also have a better understanding of, at the very least, impedance and at least the common emitter amplifier. Okay, those are the main components that you'll need for that lecture. So I hope all of you can go through and do this module and put the effort into it, because these concepts are very relevant in both rap, but also any sort of analog design you'll do either here while at UCLA in like 115A, 115B, but also just in industry if you go into RF or analog design. All right, cool. All right, thank you.